How are you, my friends? This is lecture number 19 of the Calculus 1 lectures, Higher Derivatives and Concavity. In the objectives, we will look at the second, the third, and the fourth, and higher order derivatives, and we will look at the second derivative test for local maxima and minima. We will define concavity and inflection points, and we will see some curve sketching. Now, the second derivative is easy. See, the second derivative of f is the derivative of f prime. So the second derivative here, we write derivative of the derivative of f. So we say the derivative of the function itself. So it will be the second derivative of f. The third derivative is the same idea. The third derivative of f is the derivative of the second derivative of f. So we can write it in this way. Also, the third derivative can be written as f superscript here 3, but we read it as the third derivative of f. Another way we can write, this is the nth derivative. See, the nth derivative of x will be the nth derivative, we write capital D superscript n, just to denote the nth derivative. It can be second derivative, third derivative, fourth derivative of f. And we have many notations we can use. We can use operator notation here, like this capital D. This is the derivative of x, the second derivative. Differential, we say dy over dx for the first derivative, d squared y over dx squared. See the way we write it? D cubed of y divided by dx cubed, or function notation y prime, y double prime, y triple prime, etc., etc., etc. Let's look at this example 1. Find the first 4 derivatives of the function f of x is equal to 2x cubed plus 1 over x squared plus 16x to the power 7 over 2. So we have here fraction, we have here rational power, we have integer power, everything. So you have to start with f prime by using the power rule from lecture number 7. You can write this 1 over x squared, you can leave it, or you can write it like x to the power minus 2. Easy to use the power rule. So I will do the first one here. 6x squared minus 2x to the power minus 3. 16 we leave it, 7 over 2 bring it down, x to the power 7 over 2 minus 1. So when you simplify, you get this f prime. Now find the derivative of this. Easily you can check it, please, yourself. Then you find this answer. Then you find the derivative of the second. You find the third derivative here. And then you find the fourth derivative. This is the fourth derivative of the function f. Please check this question. It's not that difficult. The second derivative test for local maxima and minima. This is very important. First, we have a function. It should be twice differentiable on the interval I. So we should be able to find the second derivative. Now we find the critical point. Remember all the critical points, critical values of C, where f prime is equal to 0. Still, we have to use the first derivative. Now, if the second derivative is positive, greater than 0 on that interval, then f of c at this point, at the critical point here, f of c is the minimum value of the function. You see here we have a minimum, but f double prime, the second derivative, is positive. So we call this concave up. The graph will concave up. We will see that in a few minutes. If the second derivative is negative, that means the graph will look like this. We call it concave down. And then there is a maximum at this number C1 here, and at this number C2. Determine where the function has local minimum, local maximum by using the second derivative test. So we have the function x cubed minus 3x squared plus 3. See, what do we do first? We find f prime. Always we have to use f prime. 3x squared minus 6x, and this is the derivative of 3 will be 0. Take 3x common factor, then you have x minus 2. Now find the critical values where f prime is equal to 0. So x will be 0 and x will be 2. So there are two critical values. At these values, either we have max or min if there is a change in the sign. Now let's find the second derivative. From f prime, we find the second derivative. So 2 multiplied by this 3 will be 6x minus 6. Take 6 outside will be x minus 1. So this is the second derivative. Let's study the function by using second derivative test. So f double prime, this is the double prime, is second derivative, positive. So we take x minus 1 greater than 0, x will be greater than 1. So in this interval, x greater than 1 means what? It means from 1 to infinity, the function f, since f double prime positive, it concaves up. You see, I will show you here. Concaves up like this. If the second derivative is positive, so there is a minimum. So there is a minimum here. At where? At the critical value in that interval. From 1 to infinity, we have 2 there. So f of 2, put 2 in the function, you will get minus 1. Now be careful here. You are using the second derivative test, but you have to use the critical values and you have to use the function itself and the second derivative. So from 1 to infinity, the function concaves up like this. So there is a local minimum at 2, the critical value. Put 2 in the function, you will get f of 2 is minus 1. This is the minimum itself. Now, if f double prime take the same x minus 1 less than 0, so x will be less than 1. So from minus infinity to 1, the function concaves down. So we have a local maximum. From minus infinity to 1, we have this 0 there inside here. From minus infinity to 1, we have the 0 there. So f of 0, put 0 in the function, you get 3. So there is a local maximum at 0, and the maximum is 3. Please study this question. Now we can see the graph here. Look at the nice graph. X cubed minus 3x squared plus 3. So at this point, see f double prime here, just a little note here. F double prime, put it equal to 0, you get x equals 1. So at this point 1, put 1 in the function, 1 cubed minus 3, 1 squared plus 3, it will be also 1. So the point 1, 1, we call it inflection point. Concavity and inflection points. Let's define concavity in this slide. Suppose we have a function f differentiable at a point A, and L is the tangent line to the graph at the point A, comma, f of A. So at this point here, there is a tangent line L to the curve at that point. Then the function f is said to be concave upward at A. So we say the function concave upward at A if on some open interval containing the A here, the graph of f, the red one, lies above the line here. See, that's concaving up. So the whole graph will lie above the tangent line. And also f double prime will be positive at that open interval. So we will have a local minimum here. We can also say the function is said to be concave downward at A if on some open interval containing A, the graph of f lies below the L. You see the graph here, the red one, lies below. So in that case, f double prime is negative, and we have a maximum. Now this is inflection point test. How do we test the inflection point? If we have a function f continuous and f w prime exists, so we can find the second derivative on an open interval containing the point A. Then A is an inflection point of f, provided that f w prime less than 0, which means negative, on one side of A, and f w prime greater than 0, which is positive, on the other side. This is the second derivative, remember. So we have an inflection point where the second derivative changes sign, or where concavity changes. We have max or min where the first derivative changes sign. Now I put here a nice graph so you can see the inflection point itself. Either we have f w prime at A is equal to 0, or f w prime at A does not exist. I put here 4 examples. Let's start with this one. Sometimes you can have a vertical tangent here. You know, when we found vertical tangents, there is an inflection point also, maybe. If this one concaves down and this is concaving up, we can have f w prime at A is equal to 0 from the second derivative, and f prime at A not 0. See, this is like a normal tangent line, but still we have concaving up and then concaving down. So this is an inflection point. This one, f w prime at A is equal to 0 from the second derivative, and f prime also at A can be 0 sometimes. This is horizontal tangent, but still we have concaving down and this is concaving up. So this is a point of inflection. Also, we can have concaving up and then concaving down. It might be a corner or a sharp corner. Still, this will be an inflection point. So the whole idea is this red line. The inflection point is the point where the second derivative changes sign. Inflection points, important remark here. A point where the second derivative is 0 may or may not be an inflection point. It's not always when we put the second derivative is equal to 0. Look at this nice example. If we have f of x is equal x to the power 4 function here, find f prime will be 4x cubed, find f double prime will be 12x squared, put f double prime is equal to 0, then x will be 0. Check now at 0. F double prime here, it's 12x squared. Below 0 and after 0, the f w prime positive and positive does not change sign. So this point 0, 0 is not an inflection. It should be an inflection if f w prime changes sign. So in one side we have concaves up, one side concaves down, then there is an inflection point. So this is not an inflection point, just a point on the graph. Now this function x cubed minus 27x, it was graphed in example 1 of lecture 18. Let's add one more question. Determine where the function here concaves up and concaves down and find all inflection points. So you can go and check, please, lecture 18, example 1. We graphed all this in details, but now we can add more about concavity and inflection points. So the first derivative was this one here, 3x squared minus 27. This is the derivative, first derivative. Second derivative will be f w prime only 6x, see? Let f w prime is equal to 0, 6x is equal to 0, that means x is equal to 0. So we have to check concavity test. Below 0, take any number negative, put it in f double prime. See, we are studying here f double prime, the second derivative. 6x, this will be negative, concaves down. If you take any number greater than 0, it will be 6x, it will be positive, concaves up. See, this is a change here. Negative, positive, or it might be positive, negative in another question. So this concaves down, this is concaves up, so there is a point of inflection or inflection point at 0, 0. Why 0, 0? We found x equals 0 from the second derivative. We replace it in the function here. It can be any number there, but it is 0 in this case. So f double prime changes sign. And here we have local max. See, at these critical values, -3, and we have here local min at 3, local max at -3. Let's see a new example here. Given the function f of x, x to the power 4, minus 2x squared plus 1. Determine where the function concaves up, concaves down, find all inflection points, also show the graph with the critical points. This is a little long question, but you can have all the ideas you need there. Let's see, this is the function f. Let's find f prime directly. 4x cubed minus 4x, see? Take 4x as a common factor, then you have x squared minus 1. You factor more, you get x plus 1, x minus 1. So the critical values when f prime is equal to 0. So there is a 0, there is a minus 1, there is a 1. See, we do now table of signs, and this is the first derivative test. So we are testing f prime. We are studying f prime in this table of signs. So we'll make another table to study f double prime. So f prime here, just put the factors here, put x plus 1. We did this many times, x minus 1. So these are negative. When you take a test point from inside the interval, when you multiply, you get f prime is negative. See, f prime is negative, the result here. That means the function f is decreasing. F prime is positive. The function f is increasing. F prime is the same, negative. The function f is decreasing, and then here the function f is increasing. So here we have a minimum, here we have a maximum, and here we have a minimum. Okay, now second derivative here. The second derivative will be 12x squared minus 4. Let f double prime is equal to 0. So 12x squared minus 4 is equal to 0. Take 4 as a common factor. Then you have 3x squared minus 1 inside the bracket. You can factor more, or you put this one is equal to 0. Take 1 on the other side, take the square root of both sides. What do you get? X equals here 1 over square root of 3 and another x minus 1 over square root of 3. See, this is what you need here. 1 over square root of 3. You don't have to know this value, 0.577. You don't have to know it. See, just 1 over square root of 3, that's a positive number. Minus 1 over square root of 3, that's a negative number. Put it here, put it there. Now take these factors from the second derivative, put it on the table of signs for f double prime. Now how do you choose the points here? Below minus 1 over square root of 3, just take any negative number very far, maybe minus 100, minus 1000, minus 7, minus 55. Put it there, it will be negative and negative. Between minus and plus, you can take a 0. That's for sure between these two numbers. So that will be negative and positive. And greater than 1 over square root of 3, you can take 17, you can take 66, you can take 90. So it will be plus and plus. So when you multiply this, you get plus. This is concaving up. See, when you multiply here, this is concaving down. And here the function concaves up. So f concaves down, where from this to this, you see that. F concaves up from minus infinity until minus 1 over square root of 3. I know the numbers are not easy, but you can still manage. Union, this is concaving up 1 over square root of 3 until infinity. Now we need the inflection points. This is a point of inflection. Two inflection points in this function. Minus 1 over square root of 3, 4 over 9. I will show you from where I get 4 over 9. The second point, 1 over square root of 3, also 4 over 9. This is a note here I wrote for you. from where we get 4/9. Take 1 over square root of 3. See, that's the x value from the second derivative. Replace it in the function itself. See, please do it yourself. 1 over square root of 3 power 4 minus 2, 1 over square root of 3 squared plus 1. When you simplify, it will be a nice number, 4/9. Please try it. Same thing here. Take minus 1 over square root of 3, replace it in the function, simplify it. You will get also 4/9. Now the graph is on the next slide. Look at the graph. Wow. This is the graph of this function, x to the power 4 minus 2x squared plus 1. The critical points, remember we have found them, minus 1, 0, 1. So minus 1, 0, 0, 1, 1, and 0. These are the critical points here in the local max, local min. And these red dots here are the inflection points. See, this is concaving up until this point, the red. Concaving down until the red, and then concaving up. So I put everything here. F decreases on this, and F is increasing on minus 1 to 0, and then union 1 to infinity. Now, please always check the playlist, Calculus 1 solved questions. You will have many questions there to understand the lectures better. This is the end of lecture 19 of the Calculus 1. Thank you for watching. If you like the video, you can subscribe and share it with your friends. I hope I can see you in another video with another topic. Thank you guys for listening.